Okay, so last 3 lectures, down to 3 lectures, the last 3 episodes of the show. So if you haven't got caught up, there's going to be a cliffhanger at the end, so you have to know everything, because otherwise the cliffhanger won't make any sense. All right. So we're going to switch gears. We're going to talk about what's called the finite element method. And what we've done so far is finite difference and spectral. And in finite difference methods, right, when you do finite difference, your problem always comes down to AX equal to B, where you discretize, use these slope formulas, build these big matrices. That's what you've got to do finite difference. Then we also talked about spectral. Well, spectral had a little bit different way of implementing things. It implemented them with these global functions, these cosines and sines, if you're doing an FFT. Or you could think about the Chebyshev method as well, which, again, expanding in terms of these functions, which were global on your domain. And in either case, they're 2 pretty good methods. Typically, you can get away with very fast speeds here, n log n. And over here, you're sort of looking at hoping to get away with order n squared. Now, on some level, the finite element method is going to be actually the slowest of all of these methods. But the big win of finite element is the fact that this is the most general method for handling any kind of PDE on any domain. Okay? So this is really the win of it. So in some sense, this is your Ferrari. Take it on a nice paved road. Okay? So if you've got a good paved road, you use this. All right. Now, if you've got a road that has a few potholes here and there and, a little bit of roughness, you might want to leave the Ferrari in the garage, take the Accord out. Okay? Still economical, pretty good gas mileage, and, if you hit a few potholes, you don't mind that much. And this is kind of like a tank. It's going to be the slowest, but you can put anything in front of it, go right over it. Okay? So, what kind of problems can it handle? Well, here's one, since a lot of you are in AA. Suppose I wanted to solve for the airflow over a wing. Now you can imagine I could have some nice flow like this. Here's my wing. Here's how the fluid flows over it. You could also imagine you have a situation with a higher Reynolds number where you actually get turbulence forming at the back of this wing. Okay, good wing. What, are you guys making fun of my wing?
No.
No, is that a good wing, Pierre?
He was fun of it.
He was making fun of it?
Looks like high lift.
Well, hey, I'm just saying it's a nice, beautiful wing. It kind of looks like maybe a little fat. Maybe you want to fly with that fatter wing. But when you go to a problem like this, here's what's interesting. This wing, you're pretty much assuming there's no fluid flow inside of this wing, right? So this wing in your computational domain represents the boundary condition. In particular, when you go to the wing, there's typically what's called a no-slip boundary condition. That's the idealization. So your velocity profile across this wing does something like this. Okay? And typically this region of transition is called a boundary layer. And you kind of want to know what happens over the wing with the airflow. But now here's what's interesting. These methods we've been developing, finite difference, spectral, there's always this boundary away from things. But here we're putting smack in the middle of this thing, a boundary that you have to handle. And it's not just a simple boundary, right? I mean, this is we would like to put in complicated wing shapes into here. We could even think about, suppose I wanted to know about the properties of a biplane. Right, Pierre? Biplane? There we go. All right? So you can imagine much more complicated boundary conditions here. that we have to deal with. In fact, there's a boundary here, here, here. There's this domain. These are complicated shapes. So first of all, if you try to do this spectrally is assuming, first of all, you have periodic boundary conditions. Second of all, you can't even put holes in the middle of this domain. That's one thing. So you can't use spectral on a problem like this. Finite difference, you could maybe think about putting the boundary condition in, but what do you have to do around this wing? Well, when you discretize, you're always using delta x's and delta y's, and delta x's are the same. So if you were to try to put a grid around this wing, draw it up here, you'd say, okay, you know, around this wing I have to, here's my dx's, and then here's my dy's. So the best you could do for describing this wing is to say, well, there's a point on it, there's a point, there's a point. You try to just get the nearest point. So these points would sort of be the nearest point to defining the wing. That's not a very good representation of the wing in general. And in particular, well, you can say, well, I can just crank down my resolution. But then you're cranking down your huge amount of resolution around these wings, and out here, you don't need it. But you're paying the price of doing that. Okay? So neither method is going to be very good. And this is really the introduction of what is called the finite element method, which is to say, well, the finite element method just actually builds around what you've got. What it does is it takes its domain and it says, okay, you got a wing in there? Here's what I'll do with it. I will basically discretize this wing in some fashion, put a bunch of points on here, and then what it will do is draw a bunch of triangles off this thing, where the triangle here, the line here, actually, so you're interpolating around this wing, and you basically are building triangles. So every point on the triangle is a point you're going to solve for. Oh, anyway. Okay? This is kind of the basic idea of this thing. To make a grid or a mesh that actually conforms to your boundary condition versus trying to make your boundary conditions conform to your mesh. Okay? It's a different philosophical point of view. So this is kind of what you're really going to do, is you're going to use some approximating functions in here, which are these triangles, connected to this region. And in the end, what you have to solve for is all these points. Every point, and so eventually it's going to be, again, a big old ax equal to b solve again. Okay? Now let me just show you one picture of something that you might do. And the beauty of this method is that, in fact, there's a lot of commercial packages available. Here what I've done is just drawn a simple example of these three complicated domains and used one of these packages to generate a mesh. And here it is. So here's the mesh. Here's the triangles everywhere. Now the interesting thing you'll notice about this package, what a lot of them do automatically, is where you get corners and edges, turning points, you get better resolution. So a lot of these packages automatically account for the fact that you have a region of rapid transition here, here, on these corners here, and then it makes smaller triangles here, but over here where nothing much is going on, around these edges, pretty big triangles. Okay? And every point on the triangle is a point you're having to solve for the velocity of a fluid, for instance, if this is your airplane right there, which probably wouldn't fly. Okay? If that was your biplane, you'd probably stall and crash and stuff. Okay? All right. So there are some general features we want to talk about then with this method, and we're going to go through and kind of go over each step as we in this series of lectures for the week. Okay, so finite element method. What are the steps involved? So let's write them down. We'll do about half of them today, the other half on Wednesday, and then I'll actually pull up my computer. We'll put some examples in there. Okay, first, discretize your domain. This is the first thing you're doing here with these two. But now the discretization is much more sophisticated and advanced. You're taking your domain, you're breaking it up with a bunch of triangles, putting them everywhere, connecting them up. This in and of itself is a pretty high-end job to do. This is why you rely on packages to do it for you. You typically don't write your own program to do this unless you're doing research in this area. Okay? Because it's just a lot of work. And there's a lot of programs out there that are really good for doing it for you as is. Second, you select your interpolating functions. So what I showed over there was these patches of triangle. And so that's one interpolation of what the solution is doing. I'm saying on this little area, I'm approximating the solution with this triangle, with some value in that triangle. Okay? And of course the solution isn't quite that, but I'm going to interpolate the values according to whatever function I choose in there. And we'll talk about how to build that. So then you derive what are called the characteristic matrices and vectors. In other words, your AX equal to B. So you derive what these components should be, and then you assemble them. It's a big task to do this. You'll see on when we write some of these down on Wednesday. The AX equal B system is this huge thing that you have to do. Okay? But once you do that, it is just AX equal to B, and you solve AX equal to B by just saying that. And then you're done. Okay? So we're going to talk about these two steps today, which I suppose I could call 1, 2 instead of ... Everything else had numbers. Okay? 5 steps. All right. Domain discretization. In fact, I'm not going to say much about this, what the algorithm is to do this, except there are some very important features of this domain discretization. First, if you're using triangles, for instance, the width and height are roughly the same. Okay? So in other words, you know, triangles that look like this or like this are fine. But when you start doing triangles like this, no. Okay? So you don't want tall, thin triangles. You just basically want sort of some proportionality there. You want them to be, you know, widths and heights should be about similar. They're not the same, but okay. Okay. The shapes. So all shapes. Shapes is not spelled S with a SP. It's actually spelled with S-H-A. All shapes should be polygons. In other words, when we take a wing like this and we discretize it, what do? Well, we take this wing and we fit some polygon through it so that it describes the nice shape of this, whatever structure's in there. The idea is you approximate it with some kind of function, and then that gives you the ability then to put your triangles in, which are basically connect the dot type things across here, and then the triangle coming off here, going out into your computational domain. Okay? Right? And final piece. Use a commercial package to do this. What are the commercial packages? MATLAB has the PD toolbox. There's also FemLab. FemLab stands for Finite Element Laboratory. And in fact, FemLab is built out of MATLAB. MATLAB used to have the PD toolbox. The PD toolbox got developed for MATLAB, and the people who built it said, we could just spin this off on our own. So the PD toolbox is a really low-level version of FemLab. And since then, FemLab has taken off and developed their own product. It used to run off of MATLAB as a platform. Now it's completely independent. Okay? There's also ANSYS. ANSYS, is that used in your department, right? A bunch of people there. So, pick your poison. Each one of them has its strengths, weaknesses, but for the most part, they're going to get this part right. This is pretty standard stuff. Discretize your domain. And the idea is you're going to somehow specify your boundary conditions, everything like that. You give your domain shapes, and boom, you're going to just say, give me the grid, and it's going to give you something like this. Okay? Now, the thing about a mesh like this, suppose you wanted to then, from this point on, start constructing the solutions yourself, doing some things with it. Well, you can export this grid. In other words, you don't have to proceed in the software once you have this. You can actually export this domain, use it then in your code as you see fit. Okay? So you don't tie yourself into having to use the software from here on out. You can just use the software just to generate for you your domain. Then you can do something else with it. Okay? All right. So that's number 1. 2, this is what we're going to spend the bulk of the time with today, is the interpolating functions. Okay? Let me reorder my notes. Okay, like that. And I think I am done with that. Okay. Interpolating functions are going to be a really key choice. A lot of the packages now give you choices about what you can use. And what you use determines a couple things. Simplicity versus accuracy. Okay, it's as simple as that. Okay, you can choose. The nice thing about these things being automated, though, it almost doesn't cost you that much. It might just cost you more time and computation. Okay, but here are some ideas. Some different ways to interpolate between the points. Basic finite element schemes. There's simplex elements, and what they are we use linear polynomials. Okay. Complex elements. Here you use higher order polynomials. And there's multiplex methods. Elements. And rectangles are used instead of triangles. Okay? So these are common names used for things that or possibilities you have for implementing it. And let's talk about what these things mean and how to implement them. Okay. Okay. So first of all, in one dimension, let's just take some exact solution that looks like this. The point is, I don't really know what the exact solution is. I'm trying to calculate this thing numerically. So what would you use if you had a simplex versus a complex method? Well, in a simplex method, use a linear interpolation, a linear line. So what you'd saying is, okay, to approximate this thing, I would just use that line right there. Simple as that. Okay? So between any two pair of points, I use a line if I'm doing it in one dimension. And that's a simplex method. Okay? In a complex method, what you're using is higher order polynomials. Let's just use a cubic. It's quadratic, I mean. Okay? Now I'm going to approximate this thing with perhaps something that looks like this, because I can have some kind of quadratic shape to it. And suppose I do that. This is a complex method. And you can imagine, right? I mean, you know that if you make this of higher and higher degree, you can get something that fits here better and better. So your error can drop down. Okay? In some sense here, if you do a simplex method, it's a line. Your error between what's there and what it should be can be much bigger than if you fit it with higher order polynomials. Okay? But you have to pay the price. How many unknowns here? How many there? Here you got two unknowns, A and B. Here you got A, B, and C. Okay? So whenever you, right away, the way you should think about that is, I've got, every time I do a computation, this is taking me, I have to solve for one extra variable here than here. So it's 50% more. Okay? That's the kind of computation should go in your head. If I pay this price, I get higher accuracy, but at what price? The price of having to pay for that overhead of calculating that. Okay? Now I've got 2D. So this is 1D. In 2D, a simplex method uses our triangles, where each point of the triangle is there. And what you try to do in between is these have certain values, and you are trying to basically write down the equation for the plane. Right? So you have these 3 points. There's a plane that goes between them. And what do? Well, in here, you assume your solution then, in the simplex method, is linear. But now you need A, B, and C to define that plane. Okay? So this is simplex. The complex method uses higher order polynomials. But notice here, I have 3 points. Here I have 3 points. So I have 1, 2, 3, and 3 unknowns. Everything works out. Over here, I'm going to use something with higher, I'm going to approximate it now with a complex method. In particular, I'm going to use A plus BX plus CY, same as before, plus dx squared plus EXY plus FY squared. And use now quadratic terms. Now I have 1, 2, 3, 4, 5, 6 unknowns. So instead of just knowing in the complex method these 3 points, I also have to specify 3 more points. So I have a total of 6, which nails down every one of these things uniquely. The idea, though, is there's a little bit more freedom in defining the surface. I might actually get a better fit to the data. Okay? So higher accuracy, double the number of coefficients. Finally, a multiplex, a place where you watch a bunch of movies. So it's something like that. 4 points, and you try to do it as simply as possible. And you use A plus BX plus CY plus DXY. Okay? That's your multiplex elements. So you have a choice to make when you do this. Now, almost everything we're going to be talking about is going to be having to just do with simplex. We'll build up sort of our intuition from the simplex method. Okay? Either here or here. Okay? And we'll talk about what it means to build up the right type of equations for these things, and then we'll go from there. Okay. Everybody clear with that? Happy? All right. Have I mentioned use a commercial package in a while? Because you should. Okay, so this is the underlying theory. I would never do it myself. I would just use a commercial package. Always. Make your life a lot easier. There's a lot of really smart people who spend a lot of time making a product that works really nicely. You no need to write your code to do that. Okay, let's talk about the 1D simplex. In particular, we can go back to that example there, which is you have these 2 points. Suppose this is what my solution does. And what you're going to do is approximate it with a line like this. Okay. And so what we want to do is start creating the simplex method, and we'll say, okay, what is the equation of that line? Well, my approximation is going to be ax plus b. Well, how do I determine a and b? And I'm going to write this in a little bit different formula because this tends to be the way that they write it in the finite element literature. This is that inner product. So take that vector. Oh, my bad. I have it backwards in the notes. It's supposed to be a plus bx. There we go. All right. And there's 2 boundary conditions to be applied here. This has to go through this point, has to go through that point. So the first one says that phi of I is equal to a plus b xi. Phi of j is equal to a plus b x of j. Okay. Well, I can write this as a matrix system. I can say that the vector phi is equal to matrix A times A, where vector phi is phi I, phi j. Matrix A is equal to 1 xi, 1 xj, and A itself is a b. So there's the matrix formulation of it. And it's pretty easy to show that then, well, you're trying to solve for A, which is right here. That's your A and B, right? Let me not write any further down on this thing, because you guys won't be able to see it. A is equal to A inverse vector psi, which, if you work it out, is 1 over L xj minus xi, negative 1, 1, phi I, phi j, where L is this difference. Actually, no absolute value. Just a positive quantity as it is, because xj is on the right, xi is on the left. Now, that's what A is, and once we have that, then we can think about this thing here. A is just being, so any point psi is just matrix A times vector A, little vector A. So one of the ways you can write this is the following. So phi self is equal to ni of x phi I plus nj of x psi j. Now this formulation is standard, and I'll show you why. It's a very nice way to represent these things. It's related to the Newton polynomials. Okay, here. So notice what happens. When x is equal to x of I, put an x of I here, what do you get? Ni x of I. Well, put an x of I, you get x of j minus x of I, which is L over L, which is just 1. So it just becomes 1. This becomes, put an x of I, you get x of I minus x, 0. So you just get phi I. Psi, right, which is what you expect. If you put in the x of j, then you say, okay, if I put in x of j, then put in x of j here, you get x of j minus x of j. That's 0. So that drops out. X of j here, you get x of j minus x of I, which becomes L, divided by L, 1. So just get 5j. So it goes through the 2 points. And these coefficients, okay, are what are called the Lagrange polynomial coefficients. And it turns out they are very nice computationally to work with. Okay? And that's the way we represent that function. Okay? So in this 1D simplex method, what have I done? I've told you how to write down the equation for this line. No, it's nothing fancy there. But partly, the idea is writing down the equation for that line in terms of the Lagrange polynomial coefficients is an important step because in some sense, this is exactly what, when we build up the equations, the governing equations, remember the 5 steps, we're on step 3. Step 2. Step 3 comes next where we're going to actually take an equation, discretize it, and we discretize it, we want to start using this formulation right here. Okay, that's what's standardly. Is standardly a word? That is what is standard. Dunley. Okay. You can learn English from me, Pierre. I know it inside and out. Okay? All right. So, in 1D, fairly simple, but it's just a different representation that you might not use instead of equation for a line. Okay? Now let's talk about 2D simplex. Because this is really where all the action's at. So 2D simplex. And the idea here is that let's draw the same kind of picture we did before, which is now we have x, y, and then we have our solution. And the idea is there is some solution surface here. And what we're going to do is approximate some patch of this with a triangle, with a plane. Okay? Which if we project down, there's some triangle in the xy plane. Right? So we can have our different pairs of points, xy, yi, xj, yj, and xk, yk. For each one of these points, there's a surface up here. Okay? And this surface we're going to approximate with a plus bx plus cy. Okay? And by the way, this surface up here, this is our exact solution. We're approximating our exact solution by that little piece. And in this little region here, we draw a triangular plane and say that's the solution there. Okay? Much like what we did before. Okay? By the way, this triangle down here has area S. Area of this triangle. And we say, okay, now let's go through the same procedure as before and try to write down the equations for this thing. So in some sense, when we do this two-dimensional discretization, this is exactly what we're doing right here. If you write down a 2D simplex here, you're saying, okay, I have some surface. I'm approximating that surface, solution surface, with these patching together all these different triangular planes. Okay? And the interesting thing is, right, how do you do this? Notice how the connection between this and finite difference. Suppose I have a triangular patch over here. Well, here's a solution in here, solution in here. By the way, notice, this triangle shares 2 points with its neighboring triangle. So this point here, when I'm trying to solve for it, is connected to this point here through its neighbors. A lot like finite difference, right? In finite difference, you say, okay, my derivative term relies simply on my 2 nearest neighbors. But then my neighbor relies on its neighbor. And it connects that way, cascades down. And so when we write down our AX equal to B, our AX equal to B matrix is this sparse matrix where everybody gets coupled to each other through its neighbors. Same thing you see here going on. This guy couples to this guy because they have these common triangles. Okay? And just, by the way, briefly, going back to this picture again, same thing idea here. When you discretize this thing, here's this surface, solution surface above this thing. A point right there connects to a point, over here by basically this guy is connected to this triangle. All these triangles are connected together. You can, it's the Kevin Bacon problem to an extreme. Okay? Because you connect all the way through, and all these guys are connected through their, nearing triangles. So no point is really isolated. The only thing you do know if you impose some boundary conditions, typically, for instance, I could say the boundary conditions are 0 on this edge here. Well, then these points of the triangle here, this are 0, and then you just have to determine a third point on that triangle. Okay? Same thing if you're on this thing here. Suppose this was a wing. Suppose there's a no-slip boundary condition. That means the velocity on the wing was 0. It gives you a specific value to put right there. But that value then, that boundary condition, propagates out into the rest of the domain because this 0 affects these 2 points, which then affects that one, which then affects everybody else. Okay? So your boundary conditions propagate back in. Or couple back in to some big matrix, this AX equal B that we're going to construct. But it's not as easy to see as finite difference, where it's just like nearest neighbor, and you get this really beautiful matrix structure. Well, beautiful is an exaggeration of the term, but a simple matrix structure that you can do something with. All right. So now, let's go back to here. Let's talk about approximating the solution there. And how do we do it? Well, we're saying, I'm going to let this thing be on that plane right there. And what I do know is I have the following conditions to satisfy. It has to go through the point phi I, when I'm at xi, yi. It has to go to the point psi j. And has to go through the point k. Like that. All right? So in matrix form, again you have psi is equal to A times A, where A is your A, B, C you're trying to solve for now. And the matrix A is this 1 xi, yi, 1 xj, yj, 1 xk, yk. Now, you can go through the same process that we did previously to write down the solution as the thing. In other words, write down a nice clean, I use clean in parentheses, a nice clean representation of the solution in terms of these Lagrange polynomials. And let me write down what you get. We have it there in the notes, but I'll write it down because now we have to, remember, the way you have to think about this is you're going to build a big for loop. You want a for loop to go through and write down the surface for a patching surface at every single one of these points. So what you want is a computationally efficient way to represent the data. Not, here's the right answer, it looks very simple. Is there a simple way so you can do it algorithmically? And this is the nice thing about this representation of these functions is simply a simple algorithmic way of looking at things. Why? Because each coefficient is either 1 or 0 at the points. Okay? So here's what you get. Your surface is given by n of I plus n of j plus n of k. Where now these ni's and nj's and nk's are a little bit trickier looking than before, but for instance, let me return n of I is equal to 1 over 2 times the area of that triangle projected down onto the xy plane times xj yk minus xk yj plus yj minus yk x minus xk minus xj y. So let's ask what the value of this thing is for x of I, x of j, and x of k at these 3 different points. Okay, at the point x of I, y of I, what is this thing? Put in, and hopefully I put in all my coefficients correctly. When you have x of I, at that point you get x of I here, so x of I, y of j, okay, let me see. And that's y sub j. So if you notice here, you get it becomes 1. If you go through this whole calculation and do it all out. Why is that? Unless I wrote this down wrong. But I don't think I wrote it down wrong. Okay, well, let me write this down without verifying it. This is 1 when you're at the point x of I, y sub I. It's 0 at the following points. Okay? And the reason is, it's not so simple to see, actually. When you put these things in here, when you do this all up, what this turns out to be is the surface area projected down here. It's that S. So it doesn't come out to be something really nice where everything cancels out. It's just like, okay, if you were to actually calculate this, that area of this thing projected onto the plane, you'd find that's what this thing is, or twice it, and then so it's just 1 over 2s, and then these things go out to 1. And similar results for here and for here. Okay? So the idea now is you have a method by which you can algorithmically construct this thing to write down these interpolating functions. Okay? So what we've done is we've gone through 2 parts of the list. We've said that any solution surface, we've got to figure out how we want to represent it, essentially, by using a simplex, complex, or multiplex finite element discretization on these triangles, for instance, in 2D. So there you go. There's your 2D triangle. And the representation of the solution on these surfaces is going to be given by something like this. Okay? So I know how to construct the triangles, use a package. Or at least, let's say you know, kind of at least in theory, what the idea of this thing is. Second, on those surfaces, this is the solution for all these different points. And so now the only question is, how do you tie the whole thing together? Because there's 2 things missing. One, what are the governing equations? We haven't even talked about that yet. But that's the next piece, is to say, how does this thing evolve in time or space? Well, then you have to write down, what are the governing equations? And if this is my solution patch, I have to basically take this. This has to satisfy the PDEs, right? So for instance, if I had a domain with the wing, or some object, I'm using the wing analogy too much, and that was the case in there. Suppose here's a boundary and a boundary, and then I'm trying to solve for the potential in there. Well, this has to satisfy this equation. What does it mean for this to satisfy this equation? So now you have to go back through and say, okay, what is it going to impose conditions and constraints on this thing so that this is true and also I've satisfied my boundary conditions? And we'll talk about how to implement that on Wednesday. Okay? All right. That's it for today. Office hours again this Wednesday, Friday. Remember, the homework's not due till middle of next week. Wednesday-ish. Okay? So aim for that, and I'll see you guys